Welcome back, everybody. Section 8.1 is the last section I'm going to do today, which is actually Thursday now, April 16th. It's 12:17 a.m. In the morning. Introduction to Square Roots is the order of business of Section 8.1, and we're only going to do one more section in the course after this, 8.2, and that's the end of Math 082 as far as the sections are concerned. A good place to start out in section 8.1 is to just look at the first 20 perfect squares. This is something that we've already looked at when we were factoring the difference between the squares, binomials, recall. But it's good to just rehearse the first 20 perfect squares. So if you take 1 and square it, you get 1. 2 squared yields 4. 3 squared gives you 9. 4 squared, 4 times 4 is 16. 5 squared, 5 times 5 is 25. So all these numbers to the right of the equal signs are called perfect squares. 6 squared, 6 times 6, 36. 7 squared, 7 times 7, 49. 8 squared, 8 times 8 is 64. 9 squared is 9 times 9, or 81. 10 squared, 10 times 10, 100. 11 squared, 11 times 11 is 121. So 121 we say is a perfect square of 11. 12 squared, 12 times 12 is 144. 13 squared, 13 times 13 is 169. 14 times 14, 196. 15 squared, 15 times 15 is 225. 16 squared, 16 times 16 is 256. These are all perfect squares. 17 squared, 17 times 17 is 289. 18 squared, 18 times 18 is 324. 19 squared, 19 times 19 is 361. And 20 squared is 20 times 20, or 400. So, ladies and gentlemen, I have listed the first 20 perfect squares. When working with square roots, it's wise to be familiar with your, with your perfect squares, at least up to 20 squared. Okay, now that we've addressed our first 20 perfect squares, we can begin to look at the square root function in mathematics. This function here, ladies and gentlemen, this symbol is called the square root symbol. And in general, how does the square root work? Well, it's pretty simple. The square root is, this square root function is the inverse operation of squaring a quantity. Just like addition and subtraction are inverses of each other, multiplication and division are inverses of each other, the inverse of squaring a quantity is the square root function, and vice versa. Basically, the square root works this way. If I was to take the square root of a perfect square, like how about the square root of 4? Well, ladies and gentlemen, we just discovered that 4 is the perfect square of the whole number of 2. And so therefore, the square root of 4 is really equal to the square root of 2 squared. Well, here's how it works. When you take the square root of a perfect square, okay, both the square root and the perfect square disappear, because square rooting the square of a quantity are inverses of each other. So square rooting is the inverse of squaring something. And for that reason, think of the square root and the square as kind of like canceling each other out or nullifying each other. And so the square root of 4, which is the square root of 2 squared, really simplifies down to just 2. Let's try another one. The square root of 9. Well, 9 is the perfect square of 3. So the square root of 9 is really the square root of 3 squared, which really simplifies down to just 3. Square root of 25 is going to be just 5. Here's another way to check your square root simplification when you get done. The square root of 4 is 2. Why? Because if you take 2 and square it, you get back 4. The square root of 9 simplifies down to 3. Why? Because if you take 3 and square it, you get back 9. The square root of 25 is 5. Why? Because 5 squared would give you back 25. So this is how the square roots work. The square root of 100 is really the square root of 10 squared, or just 10. The square root of 121 being a perfect square of 11. So the square root of 121 simplifies down to just 11. The square root of 400 simplifies down to just 20. And so, ladies and gentlemen, you're seeing how the square root function works. Now, what if I was to take the square root of a non-perfect square? In other words, the square root of 2. 2 is not a perfect square of a whole number. So when you take the square root of a number that's not a perfect square, you're not going to get a nice whole number like we did with all these examples up here. You're going to get a decimal. In fact, the decimal is neither going to terminate or repeat. It would just keep rambling on and on and on in a haphazard fashion. So the square root of 2 is going to be a decimal that goes on forever, never terminating and never repeating. We would probably round the decimal off to maybe 2 decimal places and call it about maybe 3 decimal places, 1.414. But in reality, the decimal of the square root of 2 goes on forever, and because it never terminates or repeats, we would classify the square root of 2 as an irrational number in mathematics. So this is classified as being an irrational number. Remember, an irrational number is any number whose decimal neither terminates or repeats. Now, ladies and gentlemen, we're not really going to work with the square roots of non-perfect squares too much in this class because we're not supposed to be using any sort of electronic device or calculator. And so when we work with square roots, they're going to be square roots of nice perfect squares for the most part. Okay, when you stay in this math business long enough, eventually you'll be able to use a calculator in higher level courses, in which case you would then be able to work with the square root of non-perfect squares. Okay. All right. Let's try to simplify some more square roots. Okay. Now, ladies and gentlemen, this is a very important cautionary note involving square roots. If you try to take the square root of a negative number, the square root of a negative number, for our purposes being elementary algebra, is classified as being undefined. It's not a defined real number. In fact, it turns out to be what's called an imaginary number or complex number. We don't study those types of numbers in Math 082. You will touch base with them a little bit in intermediate algebra, Math 120. So the square root of a negative quantity, for our purposes, is classified as being undefined. So therefore, like if I give you the square root of like negative 4, we say that this is undefined. Stop and think why it is defined. If you were to say the square root of negative 4 is equal to negative 2, that is not correct. Because if you take negative 2 and square it, you get back positive 4. You don't get back negative 4. That's why the square root of negative 4 is undefined. It's not equal to negative 2, and it's not equal to positive 2 either. Now, what if we have a negative sign appearing outside the square root? Is it still a defined real number? Well, as long as we don't have a negative quantity underneath the square root, it's always going to be a defined real number. So the opposite of the square root of 4 would be the opposite of 2. Because remember, the square root of 4 is 2, and the opposite of 2 would be negative 2. So notice these are a night and day difference here. The square root of negative 4 is undefined, but the negative of the square root of 4 is defined to be negative 2. So again, whenever you take the square root of anything that's negative, it's always undefined. But if your negative sign appears outside the square root, not underneath the square root, then you could get a real number result, which is defined. All right, so let's try a couple of these. So what would this simplify to? The opposite of the square root of 256? Well, 256 is a perfect square of 16. And so therefore, the square root of 256 is 16, but we have the negative sign outside the square root, so the negative sign just comes along for the ride. So the simplification of the opposite of the square root of 256 is negative 16. If I had the square root of negative 256, now because the negative sign appears underneath the square root, we would classify this as being undefined. Not a real number. Could you have fractions underneath square roots? The answer is certainly. If I have the square root of 9 over 121, well, notice, ladies and gentlemen, after a little thought, 9 over 121 is really the fraction of 3 over 11 squared. Because 3 11ths times 3 11ths is 9 over 121. So the square root of 9 over 121, which is really the square root of 9 11 squared, simplifies down to just 3 11ths. That'd be your answer, 3 11ths. What's the square root of 1? Well, the square root of 1 is just 1, because 1 is a perfect square of itself. What's the square root of negative 1? Undefined. Because again, you cannot take the square root of a negative number and get a defined real number. So this is how square roots are working here so far. All right, what would be negative square root of 100 over 225? Well, 100 over 225 is really 10 over 15 squared, because 10 squared is 100 and 15 squared is 225. So the square root of 100 over 225 is just going to be 10/15ths. And you have to bring the negative sign along because it's outside the square root. That's how that simplifies down. All right. Ladies and gentlemen, you could have variables that occur underneath square roots. So if I had the square root of 25x squared, what would the square root of 25x squared simplify down to? So if the instructions say simplify, what would this simplify to? Well, do we have any perfect squares underneath the square root? Because if we do, we need to extract them from underneath the square root, because you cannot leave a perfect square underneath the square root and call it simplified. 25 is a perfect square of 5. X squared is obviously a perfect square of x. So using properties of exponents, I can rewrite the square root of 25x squared as the square root of 5x squared. Well, ladies and gentlemen, the square root of 5x squared simplifies down to just 5x. And so the square root of 25x squared simplifies down to just 5x. Why? Think about it. Because if you take 5x and square it, you get back 25x squared. All right, how about the square root of x to the 6th power? Well, since it's a square root, we're trying to find any perfect squares that are underneath the square root. X to the 6th is a perfect square. If you think about it, 2 divides into 6 3 times. So another way to rewrite x to the 6th power is to rewrite it as x cubed squared. X cubed squared is really x to the 6th power. Well, we're taking the square root of a perfect square. And so the square root of x to the 6th power, which is really the square root of x cubed squared, simplifies down to just x cubed. All right, so how about the square root of 36, a to the 8th and b to the 4th? Well, we're underneath the square root, so we're searching for perfect squares. Well, 36 is the perfect square of 6. A to the 8th power is really the perfect square of a to the 4th power. Notice a to the 4th power squared is a to the 8th. B to the 4th power is the perfect square of b squared. And so using properties of exponents, ladies and gentlemen, we can consolidate the quantity underneath our square root, and we can rewrite it really as 6a to the 4th b squared entire quantity squared. Well, the square root of a perfect square, these operations undo each other, so this simplifies down to just 6a to the 4th b squared. And so there's your answer. So the square root of 36a to the 8th b to the 4th, think about it. If you take 6a to the 4th b squared and square this entire quantity, you will get back 36 a to the 8th b to the 4th. So hopefully, ladies and gentlemen, we're starting to see how square roots work a little bit here in general in section 8.1. I think that's good enough for our purposes in this section. We're not going to go really that deep into square roots. We're just basically just going to introduce ourselves to the function here in 8.1. 8.2, we will show you a little bit more in-depth simplification of square roots by introducing you to a couple of properties on the product rule and the quotient rule involving square roots. But I'm going to call it quits here for section 8.1. Well, take care and try to stay up with the course. We're almost done with this course, ladies and gentlemen. We only have one more section, 8.2, to wrap, and I will do so next week. So stay healthy and stay safe.